This lesson will investigate the exponential transformation process. There are many tools that manage the brightness and contrast of our data, and this is one of those processes that does that. Now, looking at the process itself, if you've never encountered it, just as I did when I first tried to use it, there isn't a whole lot of information here. Trying to discover what it does just by looking at it and reading these things is not terribly useful. Unfortunately, there is no documentation that goes along with it to give us a little more information. So if you didn't already know what these functions mean, the power of inverted pixels, that sounds really cool, I guess, but if you don't know what it does, then what we should do is find a way to discover what it does. So I could make this section very brief. I could just show you what the thing does and what kind of images you might want to use it with, and it could be a 2-minute section. Instead, I want to do the harder thing, which is to show the process of discovering how something works, because that's beneficial in general to using PixInsight or any other astronomical software. But then on top of that, of course, is that once we've discovered the behavior, then we can delve a little more deeply and understand how it works, the pros and cons, and what situations it might be more powerful with, and then hopefully gain insight into what these parameters are. Because if we don't know what power over inverted pixels is, understanding how these parameters might affect that thing that we don't know is yet an additional complication. So we've got to figure it all out. Now, as it turns out, it is inscrutable in the sense that only by knowing what exactly this tool does could you possibly figure out what these parameters are. So I'm going to get there, but I can still discover with you the behavior of this tool, and then it'll give us some insight into how to go forward. So the functionality here is one where we could guess that this is probably going to brighten an image. An exponential function is something that rises rapidly, and so I would guess, just by looking at the name, that this is probably going to be some brightening method of images. I can also see it has a lightness mask, and that, again, would clue me into the fact that it's very likely this is meant to brighten faint things and not bright things, because there's a lightness mask. Now I'm going to turn it off for the moment, and we're going to try to discover what it does without the lightness mask, and then, of course, we can turn that on and get that additional functionality. So I can apply exponential transformation to any image I'd like and try to figure out what it does. But I think by far the best method is to apply a tool, a function, to an image that has all brightness levels. And that way we can see at every brightness level what it does. So I'm going to transform this very nice astronomical image into simply an image that has all brightness levels, and that's a gradient. A grayscale tablet, as I've demonstrated in earlier sections, is a very powerful way to figure out how a tool works, what something does. So to generate a horizontal gradient, all I need to do, and I demonstrate this in the pixel math section, so review that if you have not seen it, is use the function which is the normalized position here of an image. So if I am inserting the value equals the normalized position, that means it's going to start with 0 over here because the position is 0. When it gets to the middle position, the position is 0.5, so the value will be 0.5. And then when it gets over here to 1, the position is 1, normalized, so the value is 1. This is going to create a horizontal gradient. I will drag this over here. Now it doesn't look like it's being displayed properly. That's because we still have this auto screen stretch on. If we turn the auto screen stretch off, then of course we get our very nice gradient going from a value of 0 all the way to values of 1. Now what I'm going to do is I'm going to save this image here on my computer and call it a gradient. And then I'm going to do some change to it, and then I'll save that image. What I've done is I've wrote a computer program that's going to load the two images and just graph the input versus the output. That is just so powerful to be able to do, because then you can clearly see what the thing is doing. So I know that there's a computer program, there's code, it looks all crazy and stuff. The only thing my program does is reads into images and makes a graph. In this case, the graph will be of the input versus the output, the original value versus the values that we get when we apply the function. So I actually already have gradient fit already saved. Now I need to create a file that's called test fit. That's the one that I'm going to make right now here. So this power over, I'm going to start with the other one because I think it's more dramatic. There's the other one here which is called SMI, screen mask invert. I'm not going to change any of the parameters, order 1, and I'm also going to keep a lightness mask here off. So we'll just apply it, and then we can see it got brighter. That was kind of what we predicted. But now I'm going to save this. So I do File, Save As, and I need to save it in the correct place, which is in Users here. And then we're going to call it test.fit. I may already have one there, but that's okay. By the way, PixInsight's going to complain about the fact that I'm saving this as a fit file, but I need it to be in a fit file format so I can read it in. It doesn't change the values, though. The values are still going to be normalized between 0 and 1. So now I can come to my program, and I will run my little program. These are going to be the input and output values that will be printed over here on the right if you are curious what's going on. Apparently I forgot a little thing here. Let's run that again. There we go. So here's the graph. We have the input value, that's our gradient, and then we have the output value. So this tool is one in which it brightens an image. It seems to brighten it more strongly in the mid-tone areas, and then of course it bends towards the brightest levels here, so that means it's not going to brighten the brightest things as quickly. Now that was only had the order here of 1. If we were then to increase this, let's take a step back here, we increase this to 2, like that, and I apply it again. I save this new version as our test fit, overriding the one that I already have there. I'm just going to make a new graph, basically. Then, when I run my program this time, we can see how that changed things. So I just run it again. And now you can see that obviously it gets even brighter, even more quickly. So this is obviously a brightening thing. And we should monitor the behavior of how things become brighter, of course, when using this image or using this particular method of SMI. It could be different than, for example, PIP. So let's see if there is a difference. Now I'm putting this all on my single graph there because I just want to demonstrate how things are working. Now I'm just going to change it. I'll be more ordered. I'll be more organized in a moment. All I'm going to do is run my PIP version of this here, order 2 again, and let's just see if that's any different than what we get from a moment ago. We would expect a difference. Is it more? Is it less? I don't know. But we get to discover what the answer is. So I'm just going to overwrite my test. Yeah, okay, okay, okay. And then run my program yet again. And the answer is, I don't know if I'm sorry about the colors, but we had the blue was the first one, then we had the orange one. Now look at the green. Isn't this interesting? For the PIP case, it actually starts more slowly brightening. Then it brightens more quickly, at least compared to the first order effect. Still, though, it's less bright than overall than the SMI at the same level. And then it curves towards the top. So there is a difference between the two. And I can tell then it's very likely that what we want to do is we don't want to increase the noise. We don't want to make the grainy, noisy stuff of our images to show up so much. But we know after that, after we get something signal that's brighter than the sky, we want to brighten it up. I mean, that's the whole idea oftentimes behind these brightening routines, is you want to find a way not to brighten up the noisy stuff in the image, but then anything that, is of interest, that stuff we want to brighten, except for the very brightest things, which we don't. All of that together would be the ultimate kind of brightness management and contrast management of an image. So we've discovered something of the behavior of this process, but let's look specifically about what it is doing in detail. I'm going to use an image. I'm actually going to load a project here of something I've been working on. The image that I had here I don't think is best to demonstrate this. So one moment, let me load a nice project. So here's an image of a galaxy that could benefit from this kind of treatment using exponential transformation. It is a lenticular galaxy that apparently has the remnant of an outer spiral arm, or a couple of arms that go around the outside. So that would be nice to be able to enhance that particular feature of this galaxy, and something like exponential transformation can help with that. What we wanted to do is brighten everything that is brighter than the sky up to a certain point, and beyond that point, of course, not do very much. And this will increase the contrast between the sky and all the features that interest us. So one of the things that I'm going to do right now, hopefully from the graph you'll recall that the technique that we're going to use really brightens things very, very quickly. So I'm going to make sure I'm starting from a sky background that's quite dark. And I don't want it to be 0, but I want it to be quite dark. See, I've got 0.03 here now. It started here at 0.1. So we will just raise this, and that's going to make it quite dark. And that will help us with this tool to be able to brighten, hopefully, everything brighter than just sky values. So with that in mind, I'm going to go ahead and find histogram transformation. And I'll reset this because I don't know what this was at. And let's permanently stretch that version of this image. Now, having done that, I think we're ready. And what I'm going to do is show you the manual steps of what is already bundled in this tool. Because by doing so, you'll be able to understand what the names of these things mean. So I'm going to demonstrate first screen mask invert, this method. And then we'll also instantly understand what the parameters are about as well. So that's why I want to go through it manually. You don't need to remember the steps because it is already all here in the tool. But by seeing the steps, you can see what it's doing and what these parameters are all about. So the way that many things work in PixInsight is you have your original image, which is what this is here. And I'm going to rename it A, because we're going to make a copy of it. In this other image, I'm going to call an operator image. We're using it to operate on the original. Now, it so happens that the operator image is very similar to the original, but I'm going to call it B. And the first step after making this secondary operator type image is we should blur it. And the reason for blurring it a little bit is that as an operator image, we want it not to be very noisy. Because if this had a one-to-one relationship with the original image, anything that is noisy here will also enhance the same thing that's noisy over here. And we want to minimize that effect. We don't want there at the pixel level to be a one-to-one relationship. So we need to blur this just a little bit. Now there are a number of ways of blurring images. The one that I'm going to demonstrate, though, is this multi-scale linear transform method, which is a good one to use. So I'm going to go ahead and remove the pixel level layer just right off the top. And then on the next layer up, we're going to do a very small bias in the blurring direction. So if you go the other way, you are going to sharpen the image, but we are going to go in the blurring sense. So we're going to blur the image. You can watch what happens when I apply. One of the things to also pay attention to as I do this is I am doing it on the color image. So these steps, this tool here, exponential transformation, you can do to a color image. It doesn't need to be, although it can be, but it doesn't need to be a black and white image. Having done that, let's go back and forth. So here's the before and here's the after. It's a very small blurring amount. But we shouldn't have a pixel one-to-one relationship here. We shouldn't increase the noise over here on our original image when we do our work. So what is the work? Well, the next step is to work in the inverted space. This is really weird. It seems really weird. I'm going to go ahead and invert the image by doing Control-I here and then Control-I here. Seems kind of magical. But let me just give you a sense of why this works. What we need to do is increase the contrast of bright features in the original image. Things that are brighter than the sky, for example. But think about the original image. When things are already bright, we don't really want them to get brighter. We want the effect to be strongest when things are, middle tone to faint, but not the sky. So by doing this contrast in the inverted sense, we kind of get that similar kind of behavior. Though unfortunately, as you'll see, things that are already bright, if you remember the curve, they do get, I don't have it handy here, sorry. They do asymptotically become bright towards the top end here, but bright things still do get brighter. So we're going to need to handle that in just a moment. But let's go ahead and do the operation. Now that we've blurred the image and we've inverted them, the next thing to do is to multiply them together. So that's the operation we're doing here. We just need to multiply in the inverted space A times B. So I need to get out my pixel math to do this. And we do A times B. And this first time, I'm going to actually create a new image, because I'd like to show you what it looks like and show you how it compares to the original. Oh, yeah, just do that. So the original image is here, and the inverted image is here. If we blink the two, you'll certainly see there's the before and there's the after, the increase in contrast. And then the last step is, of course, to go ahead and invert it back. So you can see that we did brighten things up rather dramatically, actually, but we also suffer an issue. And the issue is that things that were already bright, mid-tone and brighter, they did get bright enough that it's not good. It made the center of the galaxy look overexposed, and some of the bright stars, bloated compared to where they originally were. The background is also quite bright, so ultimately SMI, this particular one that I am demonstrating here, is very aggressive. And that's why you'll note that you actually are given PIP, power of inverted pixels. It's not quite as aggressive as we saw a hint of in the original response of that function, but you can see then SMI, this method, is quite aggressive. So now you know part of it. Screen, what that is the multiplication of two inverted images. It's the same as the blending mode in Photoshop. That's what the screen means here. It means multiply two inverted images. The next thing is mask. Well, that's what we need to do because you can see that it's too bright here in the center. So we need to create a mask, and that's why there's a lightness mask here. Well, to do that in the manual sense, I'm going to use the image itself as its own mask. That's what a lightness mask is. But I need to keep it in this inverted sense. So I apply the mask here, and this time to make this work correctly, we will replace the target image. So now I'm going to do A times B, but with the mask in place. That'll prevent the contrast becoming too great in things that are already quite dark. So we do this. And now I can still see features there. So I'm going to invert this back. Oh, but not with the mask in place. Oh my goodness. Let's go back a couple of... Okay. Sorry. Remove mask. Now invert it back. So now we have our brightened image. We can still see the details in the center of the galaxy. And finally, we may need to find the right sky level. But we have enhanced the ability, very subtle here because we didn't go strongly with this method, but we've enhanced this outer structure of the galaxy. That is the idea. If you look closely, what we didn't do is increase the graininess or the noise of the image. Now, some of the stars, because of the original blurring, you want to be careful and not blur too much here with that blurring part of the operator image, or blurring too much using the smoothing slider here. Because if you do so, then you're going to be operating on areas that are in the halo of bright things like stars, and you'll make them brighter. Their halos will become brighter and look kind of funny. So you want to use the smallest smoothing factor you can, that you're not enhancing the noise in the image. That's basically the game plan, the philosophy with using this particular tool. Now you might wonder then, what is the order about? Well, we were just basically doing an order of 1. Let me show you what the expression looks like at a high-level language here. We multiplied 2 inverted images together. So this is the inverse of A times the inverse of B. And then at the end of all that, we had to invert the whole thing back, so we got back to our regular space. And of course there was a mask involved in here. But this is basically the operation that we did. Those are the steps. If you want it to be a more powerful thing, you can just put another factor here for your operator image. So you would say, I want to do what I did, but on 2 times the inverted blurred image instead of 1, or 3 times. So that's where this order comes into play. And that's just going to increase the contrast that much more. And then when we invert it back, it'll make an even brighter image that much more. So now we have a final understanding of everything that is here. We know the name screen is what this operation is, of multiplying times the 2 inverted images. That is basically the screen blending mode. Then we know we need to apply a mask, and then of course invert the final result. So that's where the name comes from. You know what the order means, basically just brighter or more of that effect. And then the smoothing deals with the fact that the operator image, you don't want noise to be present in it to enhance noise that's already in the original image, so you might need to blur it. And I'm going to probably recommend almost always here, use a lightness mask for this kind of operation, because it's very likely you're going to be using this tool to brighten things that are quite faint, but you don't want the things that are already bright to become that much brighter. So the lightness mask is going to help you control that part of the behavior of this tool. So we now know enough to just think about, I don't need to show the steps here, but we can think about what power of inverted pixels means. It is basically the idea that you take your original image, which is A, and then you raise it to the power of the inverted operator image. Isn't that weird? B. This is what, and then of course you have a mask in place and you're blurring this B image and all of that kind of stuff. But this is the operation that's occurring for this thing. And it has a ever so slightly different behavior than the SMI method, which is what I showed first. The order then is you would put another factor inside here, so it could be 2 times B again, or 3 times B, and that's going to change the power of the this operand. So you can verify this by doing just as I did manually, but what I'd really like to do here is put this off to the side for a moment and examine those graphs. Let me bring them up, because now you can see the relationship between these 2 available functions. So first of all, here is the graph for SMI, and all I did is I generated these graphs as I showed earlier by just repeatedly changing an image and then saving that as the outputted result. So you can see as you increase that coefficient, that order number, then this effect of brightening becomes much, much brighter. Now if you apply the lightness mask, this is the result that you get. And you can see how you're protecting things that are going to be fairly bright, above middle gray. They become strongly protected. And so that's why that lightness mask is so critical, because we really only want this effect to be occurring something above the sky level, wherever that is, But then right up until maybe middle gray, but beyond, yeah, we don't need it to get any brighter. So I would say that almost all the time you're going to want to check that lightness mask, and it is a default. Now, the other consideration is which of these two do we choose in general? And the default is PIP, and I've got to agree with it. So without the light, well, I can either look with the lightness mask. I'm going to compare the way we would normally use it here. Let's look at the SMI. Here's the exponential without the lightness mask. That's what it looks like. And if you want to compare these, I'll show you the comparison. So here's without the lightness mask here. Here it is. The same. I'll just try to blink here. So you can see that SMI is more aggressive, just in general, but especially notice down there near the faint stuff, that turnover that tries to keep things from rising too precipitously, and PIP is very nice. And then, of course, when we employ our lightness mask, so I'll put these down here. Here's PIP's lightness mask, and here's the SMI lightness mask. So this is the difference in these two. And PIP really does, we just like this bubble here. That bubble there is wonderful. However, there might be applications where SMI could, if you need some more aggressiveness for some reason, then SMI is the way to go. At the top end, they both have pretty much the same behavior, especially when you have the lightness mask in place. So that's the difference in the two. And let me finally now show you an example where I think it is a dramatic case of how it can improve an image. And of course, I'm going to now, I think I've justified use PIP to do it. So I'm going to open a recent image. And the recent one that I want to show you is this one here. Well, I'll show you on the final. So this version of this image is how I published it. I didn't use this cool exponential transformation on the result because, geez, I really wasn't aware of it at the time. Now, I think I would. And so let me show you why. Let's pick some order. We're going to be a little aggressive about it. The idea here is to really bring out these dust clouds. But we want to do it in a way that doesn't increase the noise. And we also want to do it in a way that doesn't lose contrast, obviously, in the galaxy itself. So all of those conditions can be met if we, number one, we need to smooth a little bit so that we're not increasing the noise. And then number two, we're going to use the lightness mask. That's it. I don't need to do all those operations that you saw me do before. Now I'm just picking the one I want, the order, the smoothing. Of course, you can use previews to determine, what the best order is and what the best smoothing is, and then apply to the image. And look at that. I like it, actually. So here's the before. And if you look at the galaxy, here's the after. So what I could do, instead of using a lightness mask, I could make my own mask. If I wanted to be a little more protective of the galaxy, that might be a customized tweak. This really isn't that bad, though. I mean, I could live with that as a result. But what I really love is what we're getting here for these clouds of dust. I don't see an increase in noise, which is wonderful. So here's the before, and here's the after. So, I mean, there is going to be some increase of some features here that were very dark, the way that I had it displayed. But I think the overall result is pretty nice. And because this worked in the color domain, this was being applied to all the channels, which had the additional benefit here of going from kind of a muddiness to something a little bit more brighter brown, for lack of a better word. I was very happy to see that because, that means the color balance isn't so terrible on the image either. That's the overall idea behind exponential transformation. It seems like that was a deep dive into it, but I think my justification is if you looked at this, the function and the order and the smoothing, and you had no context of what those things meant, and then you would need to see, I think, what I just showed you to really gain some insight into what they're for and why you would choose one of those two functions over the other. So I hope you enjoyed this exploration into exponential transformation.